Good afternoon, everyone. So yes, today I will talk about the interactions between water, ice, and the solid Earth at short timescales for modern day variations in water and ice at play with the solid Earth. But first, let's take a step back a little and talk about the emergence of plate tectonics as a quantitative theory. And we've seen this figure quite a lot over the past two days, and this is, I think, one of the main contribution of Xavier Le Pichon, who first proposed a global kinematic model in which the Earth's surface could be described as a small number of rigid plates that rotate relative to each other. And this remarkably simple framework successfully explained the global distribution of seismicity, plate boundaries, and so on, and is still a very important contribution to this day. But in fact, this model was first proposed with the hypothesis that the tectonic plates were rigid. And from the very beginning, even Jason Morgan knew that this was just a simple assumption, and he wanted to see how far he could get with this simple assumption. And I think this is really translating the kind of simple physics we can do to understand to first order complex geophysical systems. But of course, this hypothesis was challenged quite fast with a number of different types of observations. The first one is that the plate motion circuits do not always close perfectly, and that suggests that we have some deformation that may occur within plates. The second observation is that we have a deformation that is sometimes distributed across broad zones rather than localized along narrow plate boundaries. But one of the main observations of the deformation of the stable plate interiors is actually earthquakes. As you can see on this figure, you have major earthquakes of magnitude 6 and above, historical earthquakes, and while most of them occur at plate boundaries, and we talked about this quite a lot this morning, some of them occur within stable plate interiors, and in continental regions, which you can see in red, and in oceanic regions as well in white. And in fact, we need to worry about those earthquakes occurring in what we consider stable plate interiors because they can cause major damage and they can have magnitudes that are 7 and above. You can see an example here for the Bhuj earthquake in 2001 in India, or the historical Charleston earthquake in the United States, causing quite a lot of damage. And what we've learned from the advance of space geodesy marked a major turning point in plate tectonics. And actually, Xavier Le Pichon was one of the advocates of space geodesy applied to tectonics from the early days of space geodesy, as he could measure plate motion with GNSS stations and also try to test this quantitative plate rigidity hypothesis, trying to measure the elastic deformation of plates. And early measurements and various measurements in space geodesy, including looking at the relative position of radio telescopes over time. Here you can see a VLBI antenna. This could give us the relative motion between two different antennas. And at first, those observations were quite sparse and also had a pretty low accuracy, and they couldn't really give us what we wanted to look at intraplate deformation. But since, I would say, the early 2000s, we have had an explosion of particularly continuous GNSS observations with a number of of stations installed globally. And also we have made major advances in the accuracy of measurements of deformation through GNSS observations. We can now measure deformations all over the world. You can see here a map of the global network processed weekly by the Nevada Geodetic Laboratory of about 17,000 stations in 2018, and now I think it's about 25,000 stations worldwide. And those stations can give us deformation measurements of a fraction of millimeter per year in accuracy. And those observations have shown us that, in fact, even in intraplate regions, the solid Earth, the plates deform, and they deform in a complex way. You can see here the velocities, the horizontal velocities here, and the vertical velocities obtained for even making the reference frame, which is the international reference frame, the ITRF 2021, which provides a stable foundation for all precise geodetic measurements and enables the quantification of Earth's deformation and plate. And in the making of this reference frame, we also had to account for and to start to model the intraplate linear and nonlinear deformation. But once we have this observation of intraplate deformation, the key question is really what drives this deformation. And there are two options here. The first one is long-term viscous or plastic deformation of the lithosphere. And if this is true, it's great because it reflects the long-term state of stress within the plates and can provide us with insights into the tectonic forces that drive plate motion. But in fact, we can also be seeing shorter-term elastic recoverable deformation of the lithosphere that can be driven by a number of processes that cause stress perturbations in time. And those include earthquakes, and we've learned about this morning already, but also oceanic and solid Earth tides, glacial isostatic adjustment in response to, since the last glacial maximum, but also internal strains within the lithosphere of thermoelastic or poroelastic origin that can be driven by temperature variations or groundwater pressure variations within aquifer systems. And it can also be linked to continental hydrology, ice, and ocean loads. And in fact, you kind of have to look into all of these different processes to try to quantify them, model them, in order to be maybe able to access the tectonic signal in intraplate deformation. And so for today, I will focus on only the continental hydrology, ice, and ocean loads. And for that, I'll take you kind of on a journey from seasonal continental hydrology to recent ice melting and to a century of ocean ice increase driven by climate change. So if we start with the seasonal hydrology, first we have to look at whether or not we can see seasonal deformation of the Earth. And if we look at a GNSS station here, located here in Lhasa in Tibet, we can look at the north, east, and vertical displacement through time. The first thing you can see is this linear motion of about 2 centimeters per year, which translates mostly plate motion. So I'm going to take this as my noise and your signal, maybe, but remove it and look at what is left. And in what is left, we can see that we have some nonlinear motions that are recorded of about a few millimeters in amplitude for the horizontal component and a few centimeters for the vertical component. And those deformations that have a clear annual signals have been related to variations in continental hydrology, atmospheric, and oceanic load. And the idea is very simple. When you have a load, water load or climate load at the surface, you will deflect the plate, and so you will record the deformation with the GNSS station. So basically, if I apply a load, then my GNSS station is going to go towards the load and down, and if I remove the load, then I will have a deformation in the other direction. So if we want to relate the deformation that we record at GNSS stations with the hydrological load, we first need a way to measure hydrological loading. And for that, we can turn to another type of geodetic observation by mapping the spatial and temporal variations of the Earth's gravity field. And for that, we use the GRACE and GRACE follow-on missions, which are satellite missions in low orbit, so about 500 kilometers above the Earth, in a quasi-polar orbit. And these missions are very simple by design because they only have 2 satellites that follow each other on the same orbit. And what we measure very precisely is the distance and the evolution of the distance and velocity and acceleration between those two satellites. And what happens when those satellites approach what we call a mass anomaly, so here a mountain with a glacier, for example, the first satellite is going to get attracted by this mass anomaly, and so its velocity and its orbit is going to change slightly, and so we can record this by just measuring the deformation. And as those satellites fly over this mass anomaly, the distance, velocity, and acceleration between them evolve, and we can take that measurements and invert for the mass, for the gravity field that can explain that. And in fact, this is very simple in design, but if we look at the raw data, this is what we obtain. And what we obtain is mostly noise in the direction of the satellite orbit with a very characteristic structure here. And we have to work a bit to try to best filter this noise to access geophysical observations of mass change. And here we've adopted a data adaptive spatial and temporal filtering to do this, but you can see that we still have some stripes here. So what I'm going to show you here is a little movie of the mass gravity change over the past 20 years, and we express this as what we call equivalent water height. So it's basically the height of the water column that would be required to explain the change in orbits that we see between the satellites. So let's go for it. So you can see that you have things that move around all the time, and you have a strong seasonal signal, for example, located in the Amazonian basin or in Southeast Asia. And you can also see a ton of different other signals. So you can pick yours, glaciers in Alaska melting seasonally, and on long term, Greenland, or even you can see that the ocean is getting yellower and yellower, meaning that the ocean is gaining mass, and we can actually measure it with space gravimetry over the past 20 years. So once we have this idea of the hydrological loading, we can try to relate it to deformation by using a theory and a model. And this model is going to answer the questions of how the solid Earth deform under surface loading. And if we go back in time and try to see where this theory comes from, the oldest mention of that I could find was actually by George Howard Darwin, so the son of Darwin, who was interested in tidal forcing, oceanic and solid Earth tides, and came up with a very simple homogeneous elastic half-space model in 1899. And now we use something that is a little more complex because we consider a spherically symmetric, non-rotating, elastic, and isotropic Earth model, so a little more complicated. But if we do this, we can actually try to predict the deformation of the solid Earth, of the surface of the solid Earth, induced by variations recorded by the Grace satellite. Sorry. And here you can see maps of the seasonal deformation of the model derived from the Grace data, and you can compare this with global networks of GNSS data. And here, the redder you are, the closest you are to the closest the model derived from Grace is to the annual GNSS observations. And so you can see that to first order, we match the vertical and horizontal deformations, but it's easier to look at a station again here in Lhasa again, the model in red that is completely independent from the GNSS observation and derives from the Grace loading of the Earth. You can see that the seasonal part at least matches pretty well the observations that we have of surface deformation. So we have a good first-order elastic model for the seasonal deformation of the Earth that is in agreement with our GNSS observations. And in fact, this model can help us understand variations in seismicity. And for that, I'm taking you to an intraplate region. So this kind of seasonal seismicity patterns had been shown before at plate boundaries, but we looked at a place where there was no other deformation than the one driven by hydrology. So we are in the central US, in the New Madrid zone, and this zone has been well known because it has had major magnitude 7 and above earthquakes in the early 1800s. And since then has had a continuing low-level seismicity up to present day. And in fact, if we look at the seismicity catalog and we try to stack everything over a year, and we look at the cumulative number of earthquakes as a function of the magnitude here as well, you can see that you have a significantly more earthquakes, in fact, in the months of July to October. And this is significant, it's not a noise. And we try to explain this by looking at a multi-technique observations. So here we have the seismicity rate, and on the right you have a stack over a year. And here you have a deformation recorded at a GNSS station, and a model derived from GRACE in red, which is in pretty good agreement. And here you have the GRACE data, and here you have stress variations driven by the GRACE model, which reach about a kilopascal annually. And what you can see is that if you stack everything over a year, things agree pretty well. Basically, you have more earthquakes when you have more deformation, and meaning that you have less load, everything's going up, and then stress variations that correlate, and this correlates with the peak stress variations as well. This is true on the annual timescale, but it's also true on a multi-annual timescale here. So what we have here is an elastic model that predicts the GNSS observation. We have also an indication that even small stress transient driven by hydrology of a few kilopascal annually can help release the elastic strain energy that must be stored within the plate, probably over a long time scale. And this is supported by other observations from laboratory earthquakes experiments, where we see an increase in modulation of earthquakes, like small periodic loading as we approach failure. But all of this has been done in a purely elastic rheology framework, and we can wonder if this is compatible at the annual timescale with other observations that we have. And in fact, through that, we can turn to the post-seismic deformation of the Earth. One of the, I think, most important figures of what I've seen in the past few years is this figure by Olga Trubienko and Luz Fretu, who I think is here, of deformation after large earthquakes for 3 major earthquakes in different regions. And those deformations are recorded by GNSS stations in the intermediate to far field, so about 100 to 1,000 kilometers away from the epicenter. And those deformations are normalized within the co-seismic. And the first thing that you can see is that for those 3 major earthquakes, so Sumatra, Maole, and Tohoku, deformation after the earthquake is pretty similar, meaning that we don't see major differences between different subduction zones. The second thing you can see is that those major earthquakes have different magnitudes and but similar response. And this means that probably in the intermediate to far field, the asthenospheric rheology is linear and not magnitude dependent or stress dependent. You can model this as a first order with what we call a Burger's rheology, where you have a fast response after the earthquake within maybe a year after the earthquake, and then a steady state deformation. And you can model this using a very simple Burger's model, where you have basically 2 different types of deformation: the long-term steady state that looks like a Maxwell, and then this Kelvin-Voigt block here, which translates an elastic recoverable deformation fast after the earthquake. And those can be related to different micromechanisms of deformation that can operate at different timescales, or various heterogeneities in temperature, pressure, grain size, water content, compositions, and so on. And what we need now is to understand if the values that we get for post-seismic rheologies, transient rheologies, are compatible with what we derive from the seasonal deformation of the Earth. And for that, we need to update our model from an elastic to a viscoelastic model, and for that, we can turn to what has been developed for GIA models, so glacial isostatic deformation. So we are going to look at the viscoelastic response of the solid Earth with Burger's rheology. And so if we test values that have been put forward for post-seismic models, you can see that if we look at a single station here in Brazil, you can see that you have a deformation, a range of models that will not fit the seasonal observations. And so we can look at this at large scale as well, using a global network of GNSS stations, and looking at whether adding viscoelastic deformation compared to the elastic deformation is going to help us improve the seasonal model or deteriorate it. And what we find is that usually it deteriorates the model, and so at seasonal timescale for hydrological loading of the Earth, a purely elastic model of the Earth is pretty accurate. What we can do is use that seasonal deformation mode of the Earth to place constraints on the transient viscosity properties that we can use in post-seismic deformation. So basically, kind of having transient viscosities that are above 510 to the 17 Pascal seconds, and also place constraints on the shear moduli. But we need to wonder now if, for the seasonal timescale, a purely elastic model is valid. What if we have decadal to centennial hydrology-driven surface loading? And for that, we can turn to recent ice melting. And this has been looked at in various places, from Greenland to Antarctica. And people have shown that you can't really model the solid Earth response to recent ice melting by a purely elastic model. Here is an example for a station in the Antarctic Peninsula, where you have in gray the observation, and in red a purely elastic model. And this is important because it means that at decadal timescales, we need to worry about the transient rheology of the Earth. So there is an emerging recognition of a viscoelastic transient response of the solid Earth for decadal timescales, yet most of the observations that have been made for this transient rheology induced by unloading of the ice have been made in regions where we have many other overlapping signals, from glacial isostatic adjustment to earthquakes to volcanoes and so on. And so those signals are quite challenging to separate. So to try to overcome this limitation, we can turn to a natural laboratory, and for that, I take you to Kerguelen Islands. So the Kerguelen Islands is a subantarctic island, which is a big marker of climate change, because it has had sustained ice loss over the past decades, facing big changes in the polar front position here, so changing temperature and precipitations quite abruptly. So if we look at the island, we can see that we have a major ice cap, the Cook ice cap, and we can look into how this ice cap has evolved recently. And we can look at this by looking at surface change over the past decades, so since 1963, because we have some archives photos that were taken for making the map of Kerguelen by IGN. We can also use satellite optical imagery, and what we get is that we have had a surface change over that period of about 30%, and that makes the Kerguelen, or the Cook ice cap, one of the fastest melting rates on Earth. And we can also look at volume change, and this is kind of the color here below, by looking at digital elevation models and differentiating them between dates. And here we've done 2000 to 2025. And so here you can see the ice elevation change in meters per year over the 25 years of observations. And so what you see is that mainly we have melting from the edges, and the Emperor Glacier here is changing volume with variation of about 10 meters per year. So now we can turn to deformation. And if we look at the only GPS station here located at Port-au-Français, what we see is no deformation. And this, you might think, is a bad news, but it's actually a good news because it means that we don't have large-scale GIM deformation over the island. And so what we can do now is move to deformation measured by INSAR. So here now we have a map of the deformation in the direction of the line of sight, but mostly vertical in that region. And you can see that over the past 10 years, from 2015 to 2025, we actually have had uplift around the ice cap of about 5 millimeters per year. And this crystal uplift might be related to the melting of the ice cap. We also have other types of signals that I won't talk about too much today, but which are related to other processes. So of course, what we can do is try to model this deformation, present the deformation as the response of an elastic Earth to the melting that we get from satellite optical imaging. If we do this and we look at a cross-section here in the island, what you can see is that the observations in gray are fairly well modeled to first order with the elastic deformation model driven by recent ice melting. But we have misfit here that has an extent and an amplitude that is difficult to predict by just changing the elastic properties of the Earth. And this is shown here, but in fact, we can move to a viscoelastic deformation of the Earth and model this as a viscoelastic deformation. And our best fitting model here better predicts the observation, as you can see in purple, but has viscosity values that are very low, an apparent viscosity of 710 to the 17 Pascal seconds for 50 years, for 70 years, historical mass change of ice mass change, and an elastic thickness that is very low as well. And so we can try to replace this in the context of what we know about viscosity of the Earth's mantle. So the Kerguelen here that we constrain, the Kerguelen viscosity that we constrain with 70 years of ice melting is very low. But in fact, we can compare this to it's difficult to compare this to what we get from GIA estimates, because GIA estimates are mostly constrained by observations that are in cratonic regions. So to try to look at something that is more, that would reflect a little more what happens for the asthenosphere, there are some considerations from small-scale convection to explain the thickness of the oceanic plates and young continental plates that can tell us that in the region we're looking at, we should have something that is of the order of 10 to the 19 Pascal seconds. Although this is still much higher than what we get from the ice unloading constraints. And in fact, this might just be reflecting something that we've seen in other regions, which translate the transient rheology of the Earth, meaning that we have a frequency-dependent rheology of the Earth's mantle that we need to map and account for. And in fact, this is still quite an open question, because we have evidence from laboratory experiments, and also from some observations, but those observations are hard to make because we don't have a lot of loads to use to make those constraints. So I think we need other large wavelength loads and longer timescales to try to continue and map the full spectrums of the Earth's mantle rheology. But before I move to that, I'll just tell you a bit more about Kerguelen, because in fact, we also see earthquakes in Kerguelen that might be related to ice unloading. And in Kerguelen Island, we are also in an intraplate region with very negligible tectonic deformation. And what we see from the single geoscope station here is our clusters of seismic activities that we have a hard time locating with just one station. But from the INSAR observations, we've seen, we've managed to observe 3 different magnitude 4.5-ish earthquakes with deep slip configurations, and we can see ruptures that are quite long from magnitude 4.5, about 10 kilometers. But in fact, if we do a slip inversion, we see that those earthquakes are very shallow, with slip at 2 kilometers depth or 1 kilometer depth, and they may be linked to the Cook ice cap melting, which has been induced for the past 70 years, Coulomb stress changings of about 1 kilopascal per year. But still, this is much open. This has been shown for GIA deformation, but for recent ice melting, we don't really know what the interactions between the ice and earthquakes are. Okay, so for the last part, quickly, I will go through a century of ocean mass. And for this, I will show something that is more related to climate. Again, as the global mean sea level observations over the past decades, and how we have a misclosure mystery. So I'll explain that in a bit. So we can measure global mean sea level through satellite altimetry, this is a volume change, and if we add up mass changes that we get from the satellite gravimetry mission for the ocean, mass increase, and the steric volume changes that we can get from the Argo float, we should be able to recover the same thing that we measure through altimetry. But in fact, and this is the difference between the black curve here and the red curve, we have a misclosure issue, and a lot of work has been done over the past few years to try to close this sea level budget, because this has implications for warming of the deep ocean, which apparently was also an interest of Xavier Le Pichon. So this has climate implications that we need to solve. But this is also dependent on the solid Earth rheology, and we need to see if this elastic standard assumption that we make when we process the data is still valid at a timescale that is 100 years of ocean mass loading. And we know this from temporal evolution of ocean mass that is reconstructed from various observations, tide gauges, but also satellite observations in the modern era. And you can see that we have had an increase in the ocean mass that we can spatialize using just where the masses are today over the past 2 decades in the GRACE data. And so now we need to have a full spectrum rheology of the Earth, a model for the full spectrum rheology of the Earth to try to capture the variations, long-term variations of 100 years of ocean mass load. And for that, we move from just the simple Burger's rheology to an extended Burger's rheology, where basically we have more Kelvin voids blocks here, and we can model this as a function of the elastic part, and we can get elastic properties from various seismic profiles, and from the viscous part, where we can, long-term viscous part, where we can get information from GIM models, a range of them. And then we need a model for transient shear moduli as a frequency-dependent transient shear moduli. And for this, we can turn to the theory of formalism that is used for seismic attenuation, because it's the same problem. We also have attenuation that depends on the frequency. And we can constrain parameters of this law using other types of observations, seismic, post-seismic, and tidal observations, to try to see the impact of including transient rheology for 100 years of ocean mass loading, and whether or not we can close the sea level budget. And in fact, here you have the amplitude of the value of the mass change over the past 20 years in millimeter per year. If you consider the Earth, as measured by GRACE, if you consider the Earth fully elastic, you get something of about 2.1 millimeter per year. If you had the very long-term GIA viscosities, you get about the same thing. But if you start including short-term viscosities that have been constrained using other types of observations, you see a jump that is beyond the uncertainty, and you have a mass change today that is about 2.5 millimeter per year. And you can look at whether or not this mass change that we derive from GRACE is the same as the one that we can get from altimetry minus the steric effect Argo. And in fact, you can see that we have closed the sea level budget. This doesn't mean that the deep ocean is not warming. It just means that the solid Earth interaction with ocean loading should be accounted for. In fact, it also means that when we look at long-term trends in the GRACE data, and we try to measure ice melting or variations in lake level, for example, we are making maybe a mistake in the amplitude of the mass change because we didn't account for the fact that the solid Earth also deforms. And this can reach about 20% in mass change. The largest source of uncertainty in all this study is still the transient rheology of the Earth, and I do believe we need more observations of that, so trying to find new ways to image this transient rheology. This also means that if today we know that for 100 years we had a transient rheological response to ice melting and ocean mass loading, we might need to revisit the way we do GIA models, because it means that at the onset of ice melting at the last glacial maximum, we actually have a fast transient response that maybe need to be taken into account and could change slightly the viscosities we infer. All right, I arrived at the conclusions. So satellite geodesy has revealed measurable millimeter to centimeter per year deformation within stable plate interiors, and it keeps doing it. And part of this deformation can be, it reflects short-term elastic recoverable deformation driven by ice and water, mass variations and other processes, rather than the forces which drive plate tectonics. This is great because it has led to an emerging field called hydrogeodesy, which is a growing field with a number of publications that is exploding, using geodesy as a sensor for hydrology. But it also is a good way to try to probe the mental rheological properties of the Earth using hydrology-driven deformation. But we need to do this in a self-consistent way, because the geodetic products themselves, in the processing, in the standard processing, the rheology is hidden in there, and so we need to do it in a self-consistent way. There are still many challenges in that field, trying to disentangle all those processes, trying to bring more observational constraints and self-consistent model, and making the link to what we know from the microphysical processes and what we can average at large scale. Of course, we need to understand interactions of these short-term processes with intraplate seismicity. I think we're still trying to document the interaction and still do not have a clear picture on that. But also we need to better understand the interactions of those intraplate deformations with plate boundaries deformation. And finally, the solid Earth and climate feedback should probably be something that we start to take into account in climate forecast. Thank you.